Hey, guess what we're going to cover in this lesson? Instantaneous rates of change, the derivative, all the things that we've been working on all year long up to this point in time. And if you'll remember, way back at the very beginning of the year, we talked first about finding the slope of two lines. Well, that's just what we have right here. We've got these two slopes. And notice if you look up here on top, this is the, let's get a little bit darker color than that. On the top, this is the change in y, and on the bottom we have the change in x. And so when we're working with these guys, that's all we're doing. As it turns out, this is the slope of a tangent line, and hey, as it turns out, this is also a derivative, which you might see in several different ways. So here's all these ways you might see a derivative. Well, what does that mean for you? That means that we can find instantaneous rates of change. You don't need to see my Dropbox folder, so let's get that off there. You can do any instantaneous rates of change by just simply finding derivatives. So let's say that we've got some random circle, okay, some random thing. Find the rate of change in the area of a circle with respect to its radius r. So what does that mean? Well, that means that a is equal to pi r squared. Okay, that's the radius of a circle. And so now it wants to find the instantaneous rate of a circle. We can do the really cool limit rule here and just have a super great time with that. Or we can follow some of our derivative rules that we just learned and we're dying to practice with. So what we would simply say is for this guy, find the rate of change in the area of a circle with respect to its radius. We would say that if we've got a equals pi r squared, then dA dr, the rate of change of the area over the rate of change of the radius. And then we just take our exponent 2 times the number in front. In this case, pi is a number, and then subtract 1 from the exponent on the r. So 2 minus 1 is r, and hey, guess what? Here is our instantaneous rate of change. Well, then it says evaluate the rate of change when a is 5 and r is 10. Hey, that's really not a problem. The rate of change then just simply means that wherever we see r, we're going to put a 5 in. So I'll just work that guy out in this kind of mustard color here. So we would say that dA dr equals 2 times pi times 5, or 10 pi. And 10 pi is a perfectly legitimate answer. There's no need to do anything else to that. It's totally fine. We could also investigate what happens when r is 10. So dA dr is going to be 2 times pi times 10, which is 20 pi. And again, this is a legitimate, real life, totally cool answer. There's no need to go throwing decimals around when it's just not necessary. So that's what these guys would look like. And so then the last question is, if r is measured in inches and a is measured in square inches, what units would be appropriate? And so in this case, then we have to really pay attention to what's going on. First off, we're told that r is measured in inches. The r is on the bottom, and then we're told that the a is measured in square inches. That's on the top, so it would be appropriate in this case to talk about inches squared per inch. Now, I know this reduces, but when you're working with a derivative, you just simply leave your units alone and don't mess with it too much at all. So area would be, or the derivative would be, inches squared per inch. Okay, so here's just a real quick rate of change problem using some of those derivative rules, and that's why we really like it.